hold on 1 second, so that we know what's going on. Alrighty. Everybody, this is Miss Jessica Green. Everyone say hi, Jessica. Yeah. Okay. She is a math teacher. Okay? She's studying to be a math teacher. And so the way that you learn how to teach math is, frankly, by teaching mathematics. And so the material that she's going to teach you guys today specifically is going to be stuff that she's already studied, stuff she's already learned from former math classes. It's kind of a recap. Opportunity to give her something to teach, and also for you to review your stuff. Another thing too, she is a fellow student, meaning that to some extent, the way that she can explain things is going to be way more recent and more relevant to the way you're going to be learning and studying this stuff. It's more fresh, okay? Because yes, I'm an undergrad student, but I took this class my freshman year, right? And so the experience of learning it for the first time is definitely more separated than in this case. Does that make sense? Okay, so what we're going to do is we're going to respect Jessica because she is an amazing and talented mathematics teacher. You're going to give her full respect. You're going to give her full attention. You're going to take full notes just as any other person who would teach you in front of this classroom, okay? And if you have questions, ask her. You want to know why? Because she's a math teacher. Yeah? All right, cool.
Yes, guys, please ask questions because if you ask questions, I learn questions. Denzel.
So just got to ask,
it's to engage your attention, so you look up here and not anything else, you know? It's a mind game. Yes. So who all's already taken Calc 3? So like 70%-ish. Kind of. So today, guys, we are learning about inner product, length, and orthogonality. Ooh. If you don't know what that is, don't worry. Hopefully you'll learn that today. So, we're going to open the marker first. Don't worry, guys. I'm really strong. So, the first definition is over the inner product. Ooh. What is the inner product? So, we're going to let U and V be, no? I'm going to pretend it's not there. Is that, can you see that?
Yes.
Oh, okay, good. B, N, R, N. B. Oh, that is really big. You're right. It's probably going to get smaller on that side, I'm not going to lie. But that's okay. The inner product of UV is often denoted U dot V. If you remember from high school, product is multiplication, which is used with a dot. So that's how you can remember the inner product. Ooh, so smart, so fancy. So, U dot V is the number UTV. The inner product is also called the dot product. And this is really large, so don't worry, I'm going to make it better for future. Oh, U, V, of U. So, I'm going to start my theorem on the next side, because, yeah. So, our first theorem is we are going to let U, V, W, B, no, I keep writing E's. It's okay. It looks kind of like an E. But
Which it comes from the Greek epsilon, which is exactly precisely an E. So.
Ooh. Wow. That's so smart. See, you guys are learning so much.
You gotta remember, you gotta raise your hand when you gotta raise your hand.
No, you don't have to raise your hand because that takes so much time. Just ask your questions because I'm not facing you. So why am I going to just stare at you? Anyways, okay. Let U, V, W be in Rn and scalar C be in R. Then our first point, A, U dot V is equal to V dot U. This is similar. Do you guys notice in math? If you multiply 1 times 2, what do you get?
2.
If you multiply 2 times 1, what do you get?
2.
Ah, they're the same. They're similar, they're not the same. So next, B. If you have U plus V times W, you also get, I think that's a U.
Yes.
Okay. U dot W plus V dot W.
Let's go.
What property would this be if we were looking at numbers? Wow. It's almost like they're synonymous. Next, we have CU times V equals. Does anybody have any guesses what this could be?
CV? CV dot U.
That's kind of all right. There's kind of 2 answers, so good job. C times U dot V and U dot CV. Now, we have our last little point section, whatever you want to call it, and that is going to be U dot V is greater than or equal to 0. Or U dot.
Oh, sorry.
That's
it's
U?
You got you. You got
Okay, that's what I kind of maybe figured after I wrote the V, because yeah.
Also the first U as well. You got.
Oh, they're both U?
Yes.
I see. So what you just learned, guys, was you can make mistakes.
Amen.
Making mistakes is how you learn.
Yeah.
U dot U is greater than or equal to 0. And U dot U equals 0 if and only if. See, notice that's how I remember this, guys. If you don't know what this is, if and only if. It's 4 words. If and only if.
Whoa.
That's how I remember that. Because I look at all the symbols and I'm like, what the heck is that? All the time. But it's okay. So U dot U equals 0 if and only if U equals the 0 vector. Now, guys, is this and this the same?
No.
Why?
Because one is a vector.
Remember that. Because if it's on an exam and you write this and not this, you will get deducted points, as I have previously experienced. Remember that. It's okay.
Actually, sometimes though. So, but when you're saying that U dot U is equal to 0, what is that? How is that different then? Why is it not 0 vector?
Well, because when you multiply 2 vectors, you get a scalar, correct? Is that right or no?
For dot product?
For dot product, yes. Because the dot product of 2 vectors is a scalar. Here, we're going to write that in our notes, everyone.
Oh, no.
The dot, you should be taking notes, because if you take notes now, when it's time to study for the exam, you won't be stressing, scrolling through all the videos, thinking, what the heck did I just learn?
You would think that.
You would think that, but as somebody who studies education and learning, it is more effective to learn if you start learning now and not later.
Amen.
The dot product of 2 vectors is a scalar. Remember that, guys. It's really important, especially when you're writing down your answers. So next, see this star here? Stars equal important. So remember, from previous experience, stars are important. So C1, U1 plus all the way to CP, UP times W. Okay, does anybody have any questions about this?
For D, why do we say the vector times itself is greater than equal to 0, and then just go ahead and say that it is equal to 0?
Well, so this one's saying if and only if the vector
okay,
is 0, and then this one is because scale it can't be negative, right? Yeah, you can't have a negative dot product. It'll always be positive. When you're multiplying a vector by itself. It's like if you multiply negative 2 times negative 2, it'll be, or like it's like squaring something. Yeah, Denzel.
So right there, you have like a linear combination.
Wait, where right there?
The star.
The star,
You have
yes.
a linear combination. So are you basically saying a span times W, basically?
I don't know. What do you think?
Yeah.
Denzel, what is a span by definition?
All possible linear combinations.
Is that every single possible, or is that just one linear combination?
I think, isn't that every single by going to P?
Not every single one. It's just a linear combination. Yeah.
Okay.
That was a good question.
Thank you.
So this is going to be equal to C1 times U1 dot W plus, I think I have space, CP UP dot W. Okay. Scott, why don't you tell us more about this?
Oh.
This wonderful straight line.
Well, how many of you remember the superposition principle?
From what? This
yeah.
class?
From one of the examinations, yes. So this idea that you can factor out the scalars. And so, do you see how what is starred isn't a new property? In fact, it is just a combination of properties. Do you see which properties we are combining to get the star?
B and C.
B and C, yes. Prem, why do you know that it's B and C?
Because it's the constant multiple, so you can like pull it out from when with C you have U dot V times C, and so you can pull out a constant multiple and multiply it across the dot product. And then B is that if you multiply the matrix or the vector inside, you can just like distribute it.
Yep.
Wonderful.
Words.
That's good. Okay. I think, should I write my next definition here or here? Left or right side? Left. Okay. Does anybody still need this? Okay, wonderful. It's okay. Oh, do you still need it? Oh, okay. Because you can also go back and watch the video. Okay. Wonderful. So the next definition, I'll write more efficiently, hopefully. The length. This is what we are defining today. Length. Or, does that say norm?
Yep.
Okay. Or norm of, so that's not of V is the non-negative scalar. Oh my goodness. Guys, I want to be a math teacher, not an English teacher, just that.
Let's go.
Because I'm not the greatest with words sometimes, or spelling, but it's okay. Of a non-negative scalar So this is the magnitude of V is defined by the magnitude of V equals the square root of vector V dot V, which equals V2, or that's V1 squared, not V comma squared. V1 squared plus Vn squared. Now guys, what does this mean? What does it mean when we have V1 to Vn? What is the n?
All the entries for all the dimensions of the vector.
Good. It's the number of V's we have total, right? Something like that.
Yeah.
Yes. Good job, good job. And magnitude of, nope, that's not it. Of V squared equals V dot V. So,
Question.
hmm.
If I took the dot product of the vector with itself specifically, and you're telling me right now that the norm of it is a square, is that maybe why part D is greater than equal to 0?
Yes. That is exactly what I'm saying. Writing on the board. Anybody else see any observations about the correlation between the first and the second parts here?
That if you square the magnitude, it'll give you V dot V, which is algebraically true.
Yes. Wouldn't that be the same as 2 squared equals, right? That's kind of what it's saying. Something like that? I like to use numbers, something of the sort. I think that was right.
I believe.
Yeah. Anyways,
One more question.
yes.
So within that square root where it has all the different
This one?
numbers of V, is that presumably all the different numbers that would make up a vector, like say the number stacked vertically in a column vector?
That would be, I don't know.
Wait, Danny, are you asking if the V1 through Vn represent the entries of your
Yes.
column? Yeah. Yeah,
Okay,
that's
perfect.
it.
Yeah.
They just correspond to the
Thanks.
Good. Wonderful. Okay. Next. Where am I? Ah. We have another star. So this one, so the magnitude of CV equals, oh, I don't like how that looks. It's aggressive. Equals, what? How would you say this? Absolute value? Yeah, that's right. The absolute value of C times a vector V. So the magnitude of CV equals the absolute value of C times V. And so, does anybody want to come up on their own with an example for this? What might an example look like? It's just some random numbers. Anyone?
4 times the unit vector equals,
What unit vector?
I don't know, 1, 1, 1. Cool.
Equals.
4, 4, 4.
Good.
Just to clarify, 111 is not a unit vector.
It's just a vector.
Because the length of it is
Yes.
not 1.
Dang.
If I remember correctly, the length of it would be square root of 2 or 1 over square root of 2.
Root 3.
Yes, root of 3. Be square root of 3. Yeah, 1 square. It's 1 square.
Yeah. That's good. So, Denzel, you said unit vectors.
Dang. I did.
So why don't we define what a unit vector is?
Amen.
Yeah.
So, a vector. Guys, do you remember Despicable Me?
Yeah.
Do you remember vector?
We will
Exactly. He defines what a vector is through his name. So, a vector whose length, maybe unit vector is vector's dad. But they don't talk about it in the movie. Because unit vector is just a little bit different version of vector. But, so a vector whose length, tie them together, whose length is 1. Is this going to be too short? Yeah. I'll just finish it up there. Yeah, we'll just do that. So a vector whose length is 1 is called a, all right, class, say it together, a unit vector. Good job, good job. This is what we are defining for this definition. So that's a good question. Is it an unit vector or a unit vector? Because it doesn't sound right to say an.
But phonetically,
Exactly.
you're producing the Y sound.
I see. This is English and math, guys. We're learning both. Unit vector. You're paying for 2 classes at once.
Oh my gosh.
Is called a unit vector. Okay, does anybody need anything else on this side?
Yeah.
No?
No, you good.
3, 2, 1. Wonderful. Yes, there is always a video. You are so right. So, I will continue the definition of unit vector on this side. So, a vector whose length is 1 is called a unit vector. The process, I don't like that there. The process of dividing a vector by, that's not a straight line, but that's okay. Dividing a vector by its own length is called normalizing. Woo. I hope I spelled this right. Normalizing. Is that under there? Yes, it is. So, what is a unit vector? And what is it called when you divide the vector by its own length?
Normalizing.
What?
Normalizing.
Good, you guys are awake. Wonderful. What? That's a great observation. Yes.
Almost.
Kind
Is
of.
every single vector a unit vector?
No.
Wouldn't it be really cool to have a vector in general, but then always have its buddy old pal that is a unit vector version of that vector? That's why we normalize.
So you're saying if I had the vector 2, 1 over 2, 1, this is normalizing it because, by its own length. Aha.
So that'd be radical 5. Radical 5. Root 5? No, that's 4 plus. Yeah, it's radical 5.
Is that right?
But Jessica,
What?
I don't understand why your 5 came from.
Where did the 5 come from, class? 2 squared plus 1 squared equals the square root of 5.
Why are we doing that?
Because,
Math.
so if we are looking to normalize the vector 2, 1, this is what we are wanting. Wait, no, that looks like that's the answer. Hold on, undo. If we are wanting to normalize this vector here, we're going to take the vector, and if we look back at our definition of length, we are going to square root of the first vector squared plus the second vector squared equals the square root of 2 squared plus 1 squared.
Isn't that how you find the direction too?
The direction comes from the vector on top.
Yeah, but don't you need to divide it by the magnitude to get the direction?
No, that's just a scalar multiple, so you're just making it so. So you have to get the direction, but then you get the magnitude.
Yeah, the scalar.
Yes, Scott. Scott is going to help.
Miss Jessica, I'm confused. We're in linear algebra, and I've never seen that before. I'm not sure.
Yeah, what's the exclamation?
What kind of vectors are these?
Oh, sorry, these are not. There we go. Sorry. What kind of vector? It's a vector.
How do I relate that to what I'm used to seeing though in this class?
Yeah,
In
what's
this
up,
class
box?
we represent the vector.
Where's
right?
my box at, man?
In this class, we do
Oh, okay. But does the
this.
notation change the actual formula?
No,
Oh, okay.
it does not.
Wait, how would you show it in that form? How would you do normalizing in matrix? How would you
It
show
would be
that?
the exact same, it just looked a little different.
It's like, you know, sometimes you look at a TV with your head tilted forward.
No.
Sometimes, but when you go to sleep, sometimes you go.
I still don't.
Exactly, yes. I really.
You mean you don't?
I do that in my drawer on my TV.
So,
It's this.
how could we maybe write this
Oh, turn.
in our linear algebra class?
Boxes around.
Would it be something like this, maybe?
Yes.
And then you gotta divide by root 5.
And then divide. Wait, how would I write that?
Yeah, that's what I'm asking.
Would you just,
That's literally what I'm asking.
it would just, it would just say the same.
Scalar multiple.
It would just look like this?
1 over root 5. Close enough.
Sure.
One.
Or
I'd multiply
multiply-
by like a scalar fraction of 1 over.
Ah.
That is an inverse.
So,
Inverse.
ah. See how they're similar, class?
Nice.
Wow. So, I'm gonna erase this
How would
part.
you?
Oh,
How
yes,
would you show that
Denzel.
in like the? How would you show that as like the superposition?
Huh?
It's like something something plus something something plus something something plus equals A N B N.
Oh, that was just the distributive property earlier.
Oh.
Do like a 6-dimensional example because I'm not sure I'm understanding.
Yeah,
how
that's
this-
what
I don't think I'm understanding either. I'm a little confusing myself.
Can
Wait.
you add like I squared?
Huh?
Let's see a vector in R5,
So,
but like linear algebra.
oh, sorry. So like 1, 2, 3, 4, 5.
Bingo. Okay, perfect.
Wait, now what?
So now, how do I normalize that?
How would you normalize this class? Let's normalize. So we have the square root of 1 plus 4 plus 9 plus 16 plus 25. Thank you, Chloe.
It's my algebra.
55. I'm gonna assume that you are correct.
I hope I'm right. Yeah.
So, if we multiply this 1 over 55, 1, 2, 3, 4, 5.
Some numbers are attacked.
Is that how you would normalize this?
Yes.
And how long is that vector you just wrote?
How long?
What's its length?
So this vector's length is the non-negative scalar magnitude defined by this. So its length would be,
Root 55.
yes.
Well, hold on a second. What is the process of normalizing even accomplishing?
Making it 1.
Turning it into a unit vector.
Yes, turning it into a unit vector, right? Wait,
Yeah.
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 So then if I have a normalized vector, how long is it?
1.
Ah.
1 unit.
Ah.
1 freedom.
1 American.
Huh?
Remember, it's degrees freedom versus degrees communism.
Because it's a unit
Exactly.
vector, right? Wait,
Yep.
yeah. Oh.
I think class proof that they understand this. Give them a problem that they all have to do.
Okay, that sounds great. All right, guys. So we're gonna normalize. Well, not we, you. You guys are gonna tell me what to write. So we have here a vector. We'll make it. We'll do 3, 2, 2,
No, but it's like
6.
Ooh.
Tricked you there. You thought I was gonna say 3. So how would we normalize this?
Square root 9 plus 4 plus 4 plus 36.
So we take our square root with what?
9 plus 4 plus 4 plus 36.
And why are we writing 9, 4, 4, and 36?
That's how you find the
To get magnitude.
And so what does this equal?
53. Square root of 53.
So what do I do next?
Now you divide the whole thing by that.
So you can divide or you multiply.
By 1 over 50?
Inverse of 53.
Times 3,
What do you mean
2,
by balance?
6.
So you multiply it by
What next, class? Or is this it?
Technically, that is a.
Yeah, now it's a unit vector because it's divided by
it's like 3 over root 50.
Wait, so what do I write next, class?
Technically, it is an improper fraction.
Exactly. So
We can properly multiply.
Multiply root. Yeah,
Multiply
multiply
root
by
53
1.
over root 53.
Multiply by 1 extra steps.
is this what you are telling me to write?
Yes.
Ah. Is this our final answer, class?
Theoretically, yes.
Why?
Yeah?
You could throw it in there.
To all
Why would I do that?
I don't
I don't want
You
to.
don't want to square root.
Because
Why?
Oh.
Don't worry.
Yeah, that's a good question. Scott, do you want to help me with anything else that I may or may not have done?
Raise your hand if you actually can do that on your own.
If you think you could be given this and end up with this by saying, let's normalize this right here, could you get to this? Wonderful.
Yeah.
Are we good, class?
Cool. All right.
Why are
Yay.
we adding the root 53 on top of the fraction? Doesn't it change the value?
This, so this is an improper fraction, and to rationalize the denominator, you take 1 over the square root of 53,
Oh, yeah.
and then
Yeah.
times itself. Because this equals 1. And then these cancel out the square root. That's really
Okay.
messy. Yeah. That's where we got that from.
My brain didn't see that the bottom 53 changed from square root 53 to 53.
Ah.
So it looked like you just added the 53.
I see. That is a valid. Oh wait, I'll erase this side first because I have one more definition to write. Actually, I have more than one, but it's okay. I'll write fast.
Stand up. Okay.
Yes, lock in class. Okay. So we just got done talking about normalizing. So what could maybe be next? Now, if you've taken Calc 3, you might recognize some of these terms. Oh, we're talking about distance. Hopefully you guys all know what distance means in life. So the distance from you to me might be a certain length, who knows? Let's see. For U, V, N, R, N, the distance between U and V, so this is what we're defining here, the distance between U and V, or it's denoted distance of U, V is the length of the vector U minus V uv equals the magnitude of u minus v. This is the distance between uv. For time, I'm going to keep going. So I think I can fit it here. So the next definition is going to be orthogonal. Does anybody remember that word?
Yes.
Good, good. Hopefully this will jog your memory. So two vectors, u, v, are in Rn, wait, yeah, are orthogonal to each other if, so there's a condition here. This is conditional. They are orthogonal to each other if their dot product equals 0. The 0 vector specifically. Ta-da!
Question.
Yes.
Earlier when you taught us what the definition of a dot product is, you pointed out that dot products spit out scalars.
That's a really good question.
So is it u dot v equals 0 vector or 0 scalar?
I don't know. I just copied and pasted the notes.
That's because I'm realizing I transcribed my notes incorrectly.
It would
So
just be scalar 0.
I see.
Silly
Do you
goose
think I'm
mistake.
making a logically equivalent sign? Is that just
Well,
wonderful?
make him happy. Since he lost his hat, he can see. So, two
Make
vectors.
sure you put that on the test, guys. That's not a face.
Bonus points?
Give him the hat.
Maybe.
Happy face.
Yeah.
Okay, next we have two more things and then Scott can come back. I hope you guys didn't need this anymore.
There's always the video.
There is always a video. Hey, maybe it'll entice you to go back and watch the video and think about what you learned.
Scott add money.
So we have one more theorem and then just a little, hopefully you guys know this. Do you guys remember the Pythagorean theorem? Good, if you don't, then I'm not sure how you got here.
I took a wrong turn.
See, no, you took the long way.
The Pythagorean theorem. Did anybody else when they were in high school think theorem and think, I don't know what that is? And now you're like, wow, I'm so smart. So, the Pythagorean theorem is two vectors, u and v, are orthogonal to each other. Wait, no. Yes, no. Are orthogonal if and only if the magnitude of u plus v squared, remember the squared, equals the magnitude of u squared plus the magnitude of v squared. Is this almost like a squared plus b squared equals c squared? Whoa. Yes, Denzel, you seemed to be thinking. Oh. Okay. That's good though if you're thinking.
Draw
Okay.
right triangle.
A right triangle.
Yes. Okay, because class, the Pythagorean theorem works on what type of triangle?
Right angle.
Right triangle.
Can I use the Pythagorean theorem on just a random?
No.
Impossible. Okay. Why do we care so much that it only works for right triangles here?
Because there are
Because the legs are what?
Orthogonal.
Okay, so now all you gotta do is put vector arrows at the ends of the legs.
hypotenuse.
Okay, so use that as a reference. Now underneath that, draw a starting vector. You're going to need a lot more space underneath that.
Wait, I'll go over here.
Yeah. So draw a starting vector.
Just a straight vector. So that was not straight. Wait.
And everyone transcribe a copy of this in your notes. Okay? It needs a direction. Great. Now, when we add vectors together, head to tail, right? So go to the head of that vector you just drew and make one orthogonal to it. That's the tail. That's the tail. Orthogonal to. Cool. Now label your two vectors, u and v. And if you're handwriting this in your notes, you don't have to do it exactly like this. Just any will be fine. Okay, and so the vector u plus v is the vector if I started at the base of u all the way to the head of v, right? Because I go head to tail. Gee, I wonder what shape is that?
A triangle.
Oh my goodness, is it any old triangle?
No, it's
Yeah.
No, it's a right triangle. Okay, so the size of u squared plus the size of v squared, and then if we know that that is u plus v, then that is the size of u plus v. Okay? So by Pythagorean theorem, it's just a restatement in terms of our vector stuff, yes?
Wonderful.
Okay, everybody give Jessica a appreciation.
I got a question.
Go for it. Ask your question.
When will the hypotenuse not just equal u squared plus v squared?
It won't.
But they're not orthogonal,
Well,
right?
it's the square root of that.
For Denzel's question, now I have some vector u. Now I just choose another arbitrary vector v. If I add those vectors up,
It's not.
u plus v, does the Pythagorean theorem even apply to this type of a triangle?
No.
No, so I'm not even concerned about this.
I mean more of like for notation of the equation, why can't we just write vector u squared plus v vector squared?
Oh, like when to say some vector, its norm squared being u dot u?
Because the magnitude of vector u, wouldn't it just be vector u? I don't know.
Think of this as a norm. The reason why we're thinking of this as a norm is because with linear algebra, we've been operating with some vectors that are far beyond spatial dimensions. Okay? And so Calc 3, we stick around with the 3 spatial dimensions because that's what we're operating in, real space. But linear algebra lets us start talking about these column vectors that could have 100 entries. You're not going to visualize a 100-dimensional space. And so if I'm going to talk about what it means to have length within that 100-dimensional space, I just need to know its norm. And so that's where the formula is going to come in handy. Yeah. Okay. Now just a few little things before we close. The content that is going to be considered new more or less. I love the handwriting. Mine's going to be terrible in comparison to this.
No. We can still read it.
Emphasis on can. Enjoy? No. Before I even write this definition, I can teach this to you without even the notes. Suppose I have a vector, okay? Let's call this vector z. Yes?
Yes.
Okay, and what I'm going to do is I'm going to ask myself, what kind of vectors are orthogonal to this vector? So say I make this vector. Is this vector A orthogonal to Z?
No,
Why not?
it's not a 90-degree angle.
Yeah, this is not 90-degree angle. More importantly, the dot product would not be 0, right? So Z dot A is not equal to 0. What about this vector W1?
Yeah, it's orthogonal.
Yes. Okay, so this is orthogonal. So I could say that Z dot W1 is equal to what?
0.
Bingo. And that tells me it's orthogonal. Is W1 the only vector that is orthogonal to Z?
No.
What if I decide to go this direction? and some vector W2.
That's still orthogonal.
Is W2 orthogonal to Z?
Yes.
Yeah, it still is, right? Because the dot product between them, Z dot W2, is still what?
0. We do the same thing.
Now, what you've learned about span is that you can scale your vectors. So if I take my W1 direction and then just decide, what if I have another vector, W3, that's effectively taking my W1 and then scaling it up by some amount. Is this new vector orthogonal to Z?
Yes.
Yes, it still is, because Z dot W3 is still 0.
Keeping the same direction.
Clearly, we can find vector sets that are orthogonal to singular vectors. And so here's what we would do. I'm going to say that I'm going to collect into a set big W. I'm going to take my W1, my W2, my W3. What do all of those elements have in common with each other?
Don't worry about that.
Orthogonal to what? They are all orthogonal to Z. If I went down this entire list and then took their dot product with Z, it would all spit out 0. They're all orthogonal. And so what I could say is, instead of listing all three of these statements out separately, I could simply say that the vector Z is orthogonal to just W, the set itself, right? If every single member of W has the property of being orthogonal to the vector Z, then I can now start using my terminology and say that Z is itself orthogonal to W. That's the definition that I was going to handwrite. And I feel like that makes a lot more sense than me printing out a paragraph. Yes?
Yes.
Okay. So, can I put the element A in W? Why not?
It's not orthogonal.
Yeah. The characteristic of what it means to be in W is that it is in fact orthogonal to Z. And if it's not orthogonal to Z, no can do. Okay? These kinds of spaces, or should I say subspaces, are special, and they are going to be special in this upcoming chapter. There's really only one chapter for this upcoming exam, and it's all on chapter 6. Now, there is some notation that you're going to need to be aware of. And I can then refer to, let me use my, okay, this is actually good. Remember how I could say there's more W's to be orthogonal to my 1Z. Now let's extend the question. Is Z the only vector that satisfies this property? No. I could simply just beep, scale it up by a tiny little bit. And so now I have some different, maybe some Y. And it's still going to have the property that Y is also orthogonal to W, yeah? And I'm going to start, now let me start indexing these things. So here's Z1, Z2. What if I started going in this direction? And I have Z3. Is Z3 still orthogonal to W as a subspace?
Yes.
It still is. Okay? And so now we've seen that if I have vectors that are orthogonal to a whole bunch of others, it goes both ways. That's kind of the entire premise of there being such a concept as a coordinate system, as it's coming from that. And so here's what we're going to call it. If a vector W, or sorry, Z is orthogonal to every vector in a subspace W of Rn, then Z like we said earlier, is orthogonal to W. Orthogonal to W. And the set of all vectors Z that are orthogonal to W, that are orthogonal to W, is called the orthogonal complement. Is the orthogonal complement. And this is the thing that Prem was asking about notationally earlier. How do I denote this specific set? I'm going to denote it like this. I'm going to take the specific subspace that I have been referring to, right? The thing that everything was orthogonal to, and then if all of my vectors are orthogonal to this, I'm going to give it this little, like, a perpendicular sign in the superscript. So this is telling me, this W perp, that's literally how you say it. Pronounced W perp. Like the perpetrator. Wow.
You got this, guys.
W perp. Okay? So the relationship between W and W perp is that this is the subspace that has all the vectors that are orthogonal to some vector. But then all of the other possible vectors that are then orthogonal to your W fit in here. They're complementary. They go with each other, okay? That's kind of like the main definition. So whether the main result for defining the perp is so that we have a more efficient way to say this. Row A perp is equal to just the null space. And column A perp is just equal to the null space of A's transpose. Okay? So we'll talk more about this. We'll resume on Wednesday. Any final questions? Yes?
Do we prove this on Wednesday?
Unfortunately, I cannot because it takes too much time, but the textbook does cover the proof. Okay, everyone, thank Jessica one more time. That was very good.